Hey, Suparna.
Hi,
How are you today?
good. How are you?
I'm doing fine, doing fine. How did your midterm go? I heard the average was 50%.
Oh my God, bro. She gave us no time. It was so bad. I was like rushing through everything. I saw a synthesis question. I was like, it was a little confusing at first. And I didn't see that she had put something up on the board clarifying it. So I just like
Yeah,
ran to H&R to get like as many points as possible. But it was so bad. I wasn't even like halfway done with my structure until like whole time. I was like, damn.
I know. And she didn't even say anything in class too, right? When she like fixed the synthesis problem on the board, like she drew that
Yeah,
arrow, she didn't say
she didn't
anything,
even
right?
say anything. Oh my God. I was like, I'm not gonna look up and watch the whiteboard. It was so frustrating.
I know. And then like someone did like go up to her and said that they didn't know that she put something on the board. And then
Yeah, like,
the Levis was like it's your fault. You should have went up to me and asked. She said that to that person.
you serious? Did she actually?
Yeah, she did. She did.
Oh my God,
It's
that's messed
crazy.
up.
Yeah, I
That's
know. And the
so
problem
sad.
set too is due this Wednesday in like
Yeah.
uh 2 days. Oh
Oh
my
my
god.
God. I
Yeah.
like took a break this weekend. I think I'm regretting that. I was like, maybe I should study OChem constantly.
Oh my god, yeah, like it's hard to take a break in summer session because everything's too fast. 6 weeks, like it's hard to take a break in the weekend. Because if you take a break, that's saying 2 weekends, like taking 2 weekends off in the
Yeah,
normal quarter system.
I didn't realize that.
Yeah, it's okay, it's okay. Are you taking any other classes, or are you doing any other extracurriculars like volunteering or
I just have
researching?
like a few extracurriculars, but they're very manageable, so it's not that bad.
I see. Yeah, dang. Am I lagging out? Because I think let me just connect to my hotspot so then.
Just a little, but it also could be my internet.
Yeah. No, no, my internet is very bad. Like from where I'm at, like in my room, so I need to connect to my hotspot. Yeah. Mm, okay. What did you want to go over today? In office hours.
Literally everything she went over on Thursday, like
Uh-huh.
heck reactions, dyings, and then could we go over like the allylic reactions, but not like the ones where you do SN2. Like you know how there's it'll be like a benzylic, something like that, and they'll be like um I thought there was no reaction because I thought it was an SN1. Like I treated it like SN1
Mm.
reaction, but
Yeah,
apparently
yeah, yeah,
that's
yeah.
not how that works. So
Right,
I
right,
want to
right.
know why that's the case. Like how do you
Uh-huh.
not get no reaction? And then yeah. And then if we could
Yeah.
also do like a little bit of like um what are those reactions? Diels-alder
Diels-alder.
or yeah,
Yeah.
diels-alder.
Hydrohalogenation, hydrogenation, thermodynamic kinetic products. There's a lot of things going on in chapter 14. Like the next midterm,
Yeah.
chapter 14 is gonna be the hardest. Chapter 15 and
Oh shit.
16, they're shorter. Like they're together. Chapter 15 and 16.
Okay.
Yeah, let's see.
Yeah, I think somebody said that there was going to be a lot of like diels-alder on her test because she loves those questions apparently.
Yeah, Deal's order is the most confusing part of the next midterm,
Oh,
like the
fun.
most challenging
That's so
part.
fun.
Everything else is like not as bad as Deal's order. Deal's order is the worst in this midterm. Let's see. Okay. Um. Okay. So, do you want to go over everything like you went over, or like do you want to
Brief like
do
review
review?
if
Okay.
you
Okay.
could,
Let's do that. Let's do that.
because I'm
Let's try to
not
speed run
really
it.
like certain on anything. I
Uh-huh.
just, yeah.
Yeah. Yeah. Let's see. Let's do this. Okay. So vinyl halides, which looks something like this, right? This right here is called the vinylic position, which is the carbon directly on the alkene. Right. This right here is called the allylic position, which is one carbon away from the alkene. This halogen here is the halide on the vinylic position. So this overall molecule is called a vinyl halide, where the halide or halogen is on the vinylic position, vinyl halide. Right. We can make an organometallic from this by doing like the regular 118A Mg ether reaction, where the magnesium is just going to insert itself between the carbon and halogen to make that Grignard reagent or organometallic reagent. Right. Yeah, we can go over the lecture participation problem afterwards too. Let's do this one first. Right. And then from this organometallic reagent here, we could do a lot of reactions like SN2, acid-base reaction. The two most important reactions that she wants you to know for this chapter are a reaction with carbonyl. Like let's say we have this carbonyl, and reaction with epoxide, opening up an epoxide. Right. Let's call this reaction A and this reaction B. So for reaction A, this Grignard reagent is our nucleophile because the atom directly attached to the magnesium is partially negative charge, right? Partial negative charge. And then our nucleophile here is this carbonyl carbon that is partially positive charge, right? So this star atom that I starred is going to attack that dot atom, but that's going to break the octet row, right? Because this dot atom already has 4 bonds, 1, 2, 3, 4. This star atom is trying to make a new bond with that dot atom. So to conserve the octet row, we have to pop this double bond onto the oxygen right there, right? And then when we do that, we connect the star and dot together from that nucleophile attacking electrophile reaction. And that's the new bond between them, new bond between star and dot. The MgBr just dissolves away in the solution in the reaction. The dot here is attached to 2 methyl groups, 1, 2, and it used to be attached to a double bond O right here, but then that double bond O got popped up to become a single bond O minus, like that. That's the end of the first step. The second step is just to clean up the O minus by proteining it with acid, hydronium ion. O minus grabs the H, the bond between that H goes onto the oxygen, and then we get our neutral alcohol here. Right. So that's the reaction A right there. Right. Where you notice that the oxygen here is 2 atoms away from the nucleophile. If you see that the oxygen is 2 atoms away from the nucleophile, then your reactant was a carbonyl, a ketone or aldehyde, right? But now let's look at reaction B with an epoxide. Right, this is the same nucleophile, the carbon directly attached to the magnesium. Now we have 2 electrophilic carbons here, the one on the left and the one on the right. What carbon do you think is going to get attacked? The less subcarbon here or the more subcarbon? Right, to think about that, think about what conditions are we in? Are we in acidic conditions or are we in basic conditions?
Will it be the more subcarbon?
Yeah, so the more subcarbon will be if we are in acidic conditions. Like if you see
Oh, we're in basic.
H2SO4, yeah, we're in
Okay.
basic conditions. Whenever you see negative charge, think of basic conditions. Negative charge, basic conditions, right? And in basic conditions, you attack the less subcarbon subside. Less carbon of the epoxide, right? So I'm just gonna dot the less subcarbon, and the more subcarbon is not gonna get attacked. Right, attack that. Break open the ring that way. Connect the star and dot, star, dot. That's the new bond between them. The dot here is now bonded to this carbon, which is bonded to a methyl group, which is bonded to an O minus, right? To make it more clear, let's say that that carbon is green right there, which is this green carbon right here, right? The red and green bond is still there. The red carbon to green carbon bond is still there. But the green carbon is attached to a methyl group, which is that methyl group, and this oxygen still, which is that oxygen bond right there. But this time has a negative charge because this bond broke off between the red carbon and the oxygen to go onto the O minus. Right. Now the second step is just to protonate that O minus to become OH with acid to get our final product here. OH. Boom, 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 OH. Right. So now in the epoxide case, we see that the oxygen is 3 atoms away from the nucleophile. If you see that the oxygen is 3 atoms away from the nucleophile, then you know that the reactant came from an epoxide. And this is good for synthesis because if you see an alcohol and new R groups in your product, then to figure out if your reactant came from a carbonyl or an epoxide is to see the distance between the oxygen atom and the nucleophile. If it's 2 atoms away, it came from a carbonyl. If it's 3 atoms away, it came from an epoxide. Okay. What was the participation problem? Can you send me that through text so that we could go over that?
I sent it.
Okay, I got it. Oh, diels-alder. Okay, diels-alder. Okay, let me airdrop it to my iPad. Okay, I'm gonna do that participation problem, the diels-alder one. Is that the only one? I'm gonna do that around 9:30 because someone said that they wanted to go over diels-alder around like 9:30 when they joined. So is that the only one that you want to go over? Uh-huh.
I think there are one more. I can send you more.
Yeah. Uh-huh. I'll go over the diels-alder at the second half of the office hours, and I'll go over everything from the beginning of diels-alder as well. Because this one
Okay.
here is a more complicated example. I'll start from the
Okay.
beginning of diels-alder and build up to this problem here.
Okay, thank you.
Yeah. And then we could also go over Heck reaction, hydrohalogenation, halogenation, the conjugate dienes. Okay, this one. Which of these are the major products these compounds are enantiomers? Oh, okay, yeah. So this is part of the same problem, right? The same diels-alder problem, the second half of it. Like the second photo you sent me.
Oh, can you say it again?
Yeah, the second photo you sent me, that's part of the same problem, right? The same
Yeah.
diels-alder
Yeah,
problem. Yeah.
it's the same problem.
We'll go over that part as well when we go over the diels-alder part.
Okay. Cool.
Yeah.
Thank you.
Okay. Yeah. Now let's go over Heck reaction really quickly. Yeah, let's try to finish. But I don't think we can, but we'll do as much as we can before the diels-alder. Let's see. Heck reaction. So this is gonna have a vinyl halide reacting with an alkene and some kind of metal catalyst like palladium or nickel. But since Levin says it's expensive in lab, she uses these reagents: 1% palladium OAC2, R3P CH3CN heat. That's going to give you a conjugated diene as a product. Right. So we already said what the product is, which is a conjugated diene. the stereoselectivity of this reaction is that you're going to make a trans or E alkene in the product. The regioselectivity of this reaction is that the less subcarbon of the alkene reacts. Okay. So let's do an example. Let's say we have this vinyl halide right here reacting with this alkene right here. And the reagents you see are the 1% palladium, OAC2, R3 phosphorus, CH3CNE. A quick way to predict the product for this, if this shows up on the reaction section, is to locate your vinyl carbon, your vinyl carbon attached to the halogen, which is that red carbon right there. This red carbon is the vinyl carbon. And locate your less subcarbon of the alkene, which is this carbon right here in blue. That's the less subcarbon of the alkene. A new bond is going to form between them, and the halogen is going to disappear. Right, so that's the red carbon. This is the blue carbon. And this is the new bond between them. And make sure that they are E. Right, this is the E alkene. Both alkenes are E. This is E. Right. So that's the quick way to predict the product for Heck reaction. Right. Okay. Do you want to go over the mechanism as well, or can you look at that on the notes and put that in the note card? Or do you want to move on to the next reaction?
We can move on to the next one. I think you're short on time.
Okay. Let's go on to the next one. Yeah, the molecular orbital, atomic orbital. Okay, let's do the SN1, SN2 reactions that you were talking about. I think for one of the reactions, you were thinking about this, right? Like no reaction, where we have a primary unhindered halide, and then we have some kind of weak nucleophile like this. You would expect that there's no reaction here, right?
Yeah.
Primary
I think I was just confused when people got like when there was a reaction. So I was like, oh, how did that happen?
Yeah. In this case right here, this is no reaction, right? Because when you think about this right here, whenever you see a weak nucleophile, that is going to want to go do an SN1 or E1 reaction, right? And then when you think of SN1 E1 reaction, what is the very first step of the mechanism? What's going to happen in the first step of the mechanism?
Leading group leaves.
Yeah, leaving group leaves. So if the leaving group leaves, what kind of intermediate will we form? What charge will this carbon have here as the leaving group leaves? Positive charge, right, which is a carbocation. This carbocation right here is just primary. That primary carbocation right there is too unstable to exist, right? So it's not going to exist, leading to no reaction. Nothing's going to happen. It's not going to leave by itself. So this reaction here is not going to happen because we do not want to form that primary carbocation. It's too unstable, right? But now, if you introduce an allylic halide like this with the same reagents, let's say water.
Wait, but isn't it still on a primary carbocation? Like, won't it still form a primary carbocation?
Yeah, this is a primary substrate, primary unhindered substrate, right? And then when the leaving group leaves, it would form a primary carbocation, but it's not only primary, it is primary allylic, right? What can this carbocation do with this alkene?
Oh, resonance. Oh,
Resonance.
I see.
That increases stability. So that makes it stable enough to exist. So that makes it able to proceed with the reaction, have the reaction go through. Right.
Oh, I was ready. Okay, that makes sense.
Yeah. Boom, boom. So in this case, you actually get two products here, right? Because you get two products, one for each resonance structure if it's asymmetrical. Right, and I'll just give you the two products here because I think you know the rest of the mechanism.
Yeah, no, I'm good. You're good. You can move on. I've got it.
Okay, yeah, right.
Thank you.
Yeah,
I
no
was just
problem.
confused because I was like, how are they just swapping out? Okay. Okay, I got it.
Yeah. It's because of this allylic component of it, the resonance. That's the new part of this chapter.
Yeah, I was trying the mechanism and I kept getting carbocations and I didn't think
Uh-huh.
like resonance was a thing. So I was like, oh, there's no reaction.
No. Yeah.
Okay, thank you.
Yeah. This increases the reaction rate, and a conceptual thing is this right here, where let's say we compare this SN2 reaction, like NaCN, with this reaction right here, NaCN. The reaction rate of the second reaction is faster, right? Because of the um, more stable substrate, right? Because it's because of this allylic component right here, right? This allylic carbon, allylic electrophile, better
Yeah,
electrophile.
isn't the more stable carbocation kinetic and then the more stable double bond thermodynamic?
Yes. The product that comes from the more stable carbocation is kinetic. The product that you get from the double bond overall at the end is thermodynamic. Right? But it's not gonna do it with this reaction. It's something else. It's with hydrohalogenation and halogenation of conjugated dienes. Do you want to do practice problems related to those? Yeah, let's do it.
Yes, if there's time, if there's time. I want
Yeah.
to
We got time. We got time. And then let's segue to diene, diels-alder, diene file, diels-alder after these two reactions. Yeah, hydrohalogenation of conjugated diene. Let's do this one first, and then let's do the second one later. Conjugated dienes. Okay. I'm gonna have you try. Okay, try this reaction here, and then I'll be right back. I'm gonna get water really quick, and then let's go over this reaction. Are you familiar with this reaction? Oh, I forgot to ask that first at the beginning. Do you know how to approach this problem?
No.
Oh, okay. So let's go over this from the beginning, right here. Um, when you see temperature right here for Levin's class, I think she gave you two, right? 40 degrees is considered hot, 0 degrees Celsius is considered cold. Did she give you any other temperature?
I don't think so.
Okay, yeah. So there's gonna be two temperatures, one hot, one cold. Different professors give different numbers. For Leavens, I think I remember saying 40 for hot, 0 for cold. When you see hot, that's gonna give you the thermodynamic product. And then when you see cold, that's gonna give you the kinetic product. And then you said this earlier already. Where is it? Okay. The thermodynamic product is going to give you the most stable double bond. The kinetic product is going to come from the most stable carbocation. Okay. Now, if you have an asymmetrical conjugated diene, right? Are you familiar with the term conjugated diene? Does that sound familiar, or do you want to go over that term, conjugated diene?
Is it okay if you give like a brief
Yeah,
review? I think
yeah,
I
yeah.
do, but again, I'm not caught up on lectures.
Yeah, oh yeah, it's okay. No worries, no worries. Um, conjugated diene is
Can you
something.
can you go back for a bit?
Yeah, sorry. When did you take 118A and who did you have it with?
Are you talking to me?
Yeah,
I took it the summer session one with
Oh
I
yeah.
forgot his
Oh, I
name.
forgot. Yeah. I remember.
Yeah, I attended
Th-
your
th-
review sessions.
yeah. That's when you messaged me on Discord.
Mhm.
Yeah. Uh-huh.
Did you have 118B with leave-ins?
I had 118A with Levens, 118B and C with Nasiri.
Oh my God.
I know. And I
How
took
did I
118A
survive?
and B after my freshman year, like during the summer before my sophomore year. And I finished 118C fall quarter of my sophomore year, and then started tutoring winter quarter of sophomore year.
Wow. You
And
came out of lead-ins wanting to do more OChem. That's crazy. I mean, Naziri. Wow.
no, because like it was actually because my friend she wanted me to go to tutoring ATC with her because usually I didn't know what tutoring was, I didn't know what ATC was, I didn't know like UC Davis had tutoring, and then I just went, and then I got an email after I passed like the series about like to become a tutor because I think they saw like my grades and then they wanted me to become a tutor, and I was thinking about it. I was like, huh, why not? I'm just gonna try it. The time requirement is like not that much. If I don't like it, I could just quit. And then once I did it, like I realized that I like tutoring a lot. And then it turned out to be like so much more from
That's
there from that
good.
point. Yeah. Right, so
Thank
oh my
you. Thank you
god.
for still doing it.
Yeah, no problem. I think there's some ATC tutors there that I know still. Do you go to the ATC drop-in tutoring in summer session like at the
I
library?
do Maria Jones. I do
Mm.
her I just finished her 5 to 6, but I do her Monday, Wednesdays, Friday
The workshops, right? Like the
online. Just
review
yeah,
workshops,
it's
like or the
yeah.
problem walkthroughs. Yeah. Those are really useful too. I remember learning from her when I took the class as well. Her and Edna, they're really good. Edna Lamson, if you heard about her, I don't know if you know Edna Lamson.
I think Edna's only for 118C.
Hmm.
I don't
Oh,
know. I
yeah,
could
that
be
was I
wrong.
think that's now, but back then she also taught A and B and C as well. Yeah, but I think she's more like Oh yeah, Maria has just got a baby as well. But Edna like also has a kid as well.
Oh, really?
Yeah.
Oh, that's cool.
Uh-huh.
I thought they're like, are they grad professors or are they?
They are specialists, so they have master's degrees in like some chemistry. So they work for I think the ATC. They're not professors, but they're like specialists for ATC with master's degrees.
Oh, cool.
Yeah. Conjugated dienes. So when you see dienes, that's two alkenes that are conjugated with each other, meaning that they are adjacent to each other. So these are some examples of conjugated dienes here, where we see two alkenes that are conjugated to each other. An isolated diene is gonna be when we have two alkenes still because that's a diene, but it's not conjugated anymore, right? They are isolated now because they can't do resonance with each other. The biggest sign here is this sp3 roadblock, blocking resonance. Right, and I think on the problem set, there is a problem that makes you list out all the conjugated dienes, or delocalized pi systems.
Yeah. She has like,
Delocalized.
yeah, and she's like, which one's localized and like,
Uh-huh.
what is it called? And it's like an alene functional group.
Right, allylic functional group. That's when you have the perpendicular p orbitals, right?
Yeah.
Delocalized pi
I
system.
didn't know they're called that. So I was like, what is she getting at?
Yeah, it's just a name, like the allyne or accumulated diene.
Yeah.
That's when you have a network of at least it could be more, 3 adjacent p orbitals, right? And you have a p orbital if the atom is either sp2 or sp. sp3 atoms would not have a p orbital, right? Oh yeah, hey Amrita, we're gonna go over the diels-alder reaction after we go over hydrohalogenation and halogenation of conjugated dienes, which we're just gonna uh, be a good segue to diels-alder. Right. So that's gonna be like boom. These are some examples of delocalized systems here. Boom, boom, boom. Right. Where we see that's a p orbital, p orbital, p orbital, p orbital, p orbital. Okay, now this one here in the middle is a little bit tricky because when you just see a carbon with a lone pair of electrons, initially that looks sp3, right? And it is sp3. But if that lone pair of electrons can do resonance, right, then that carbon is now sp2. It's like back in 119A, when you learn about hybridization, this nitrogen here of the amine with no resonance is sp3. But as soon as you put carbonyl there, allowing for resonance, that nitrogen is now sp2, right? It's that same concept, same principle, right? So we see a network of adjacent p orbitals here, at least 3. Those are considered delocalized pi systems, right? If you have 2 p orbitals adjacent, that's not enough. An allyne or a cumulated diene is when you have a central carbon that is double bonded 2 times with 2 adjacent carbons like that, right? And let's give those 2 carbons that are on the side hydrogens. The hybridization of the middle carbon is sp because it has 2 bonding groups. Hybridization of the end carbons are sp2 because they have 3 bonding groups, right? So I'm going to draw in the p orbital of the sp2 carbon like that, which to make a double bond, 2 p orbitals would have to overlap like that, right? And if this is sp right here, the central carbon, that central carbon will have 2 p orbitals. But the second p orbital here cannot be in the same place as the first p orbital, right? So that means the second p orbital would have to be horizontal. because the first vertical p orbital is already vertical. So that makes the other right carbon horizontal as well in order for it to have a double bond right there. So there are adjacent p orbitals right here, but they're not parallel, right? The like the most amount of parallelness is like the two p orbitals here and the two p orbitals here. So that's not delocalized. That's perpendicular p orbitals, which is an allylic functional group or accumulated diene functional group. I think I worked on some of the um, problem set here, which you guys could see. Like this question here was asking for delocalized pi systems, which we did the same thing. We went and found which one of these molecules has conjugated p orbitals, at least 3. And then if there's a sp3 roadblock that blocks resonance, that's not going to be delocalized. This allyne here, C, is the allyne functional group or accumulated diene. For this one here, yeah, I'll just scroll down through this. I didn't finish everything yet, but I'll just show you guys what we tried so far for the problem set here. Okay, yeah, I think we just tried those two so far. Okay, so now let's go on to hydrohalogenation. Actually, let's just do diels-alder because that's the most confusing part, right? The most confusing part of chapter 14, and then we could do hydrohalogenation and halogenation in tomorrow's office hours. We'll start from there. Hydrohalogenation and halogenation of conjugated dienes for tomorrow's office hours. Okay. So let's do diels-alder. And then we'll do that participation problem that Jane sent earlier. That is a diels-alder problem. So this is gonna have a diene, right, which we talked about earlier, which is two alkenes like this, right? And specifically, this is a conjugated diene and a dienophile like this. It's just any alkene like that. This is the simplest diels-alder reaction you'll see, right? And the mechanism is very easy, right? Everything else is just harder, like the regioselectivity of it, the stereoselectivity of it, the endo rule, exo rule. But the arrows for the mechanism here is very easy. It's just 3 arrows where this carbon will attack that carbon will attack that carbon, that double bond will shift over there. That's it. That's it for the mechanism. Right. So if I number this 1, 2, 3, 4, 5, 6, this reaction will occur under heat or light. But there is an exception, but I don't know if Leibniz went over that exception. I'll check her lecture notes and then see if she went over that exception and then go over that with you guys. But don't worry about that exception if she does not go over it. Right. And then your product will be a cyclohexene, a 6-membered ring with a double bond somewhere in the ring, where this is atom 1, 2, 3, 4, 5, 6. Right. We broke the double bond between 1 and 2 to make a new bond between 1 and 6. That's the new bond between them. To make it more clear, I'm going to color code these bonds. Right. That double bond right there is going to be, let's say, or let's just highlight it. Yellow. That yellow bond is this yellow bond right here that shifted over there. This blue bond is now over here. It's shifted over here. This red, wait, no, this pink bond right here is going to be that pink bond right there. Okay. Yeah, so that's the basics of the diels-alder. This is the most basic diels-alder reaction you'll see, right? And then these exact arrows are going to happen on all diels-alder reactions, right? Now, to explain why these arrows happen more clearly, let's see the resonance structures of the diene and the dienophile. Boom, boom, boom. I'm just drawing out the resonance structures right now. Okay. Now, we see that when I draw the resonance structures, the negative charge is attracted to the positive charge. Opposite charges attract, right? So this negative charge here will attack that positive charge. This negative charge here will attack that positive charge right there, right? And that would lead us to the answer that we predict. This cyclohexene right here, right? Because this was the nucleophile that attacked the electrophile, making that new bond right there. This was the nucleophile attacking that electrophile, making that new bond right there. Great. So that's the electronic reasoning behind it. And generally, you will see that the diene is the nucleophile of the reaction, and the dienophile is the electrophile of the reaction. Right. So the reaction rate of diels-alder will increase when you have something called an EDG on a diene and something called an EWG on a dienophile. Right? An EDG is going to be, let's say, electron donating group. Right? A group that's able to donate electrons. An EWG is going to be an electron withdrawing group, a group that withdraws electrons. Right? Have you guys been like exposed to this term yet? EDG, EWG? Does that sound familiar? Yeah. Okay. So
Can you go
to
up very quick
yeah,
when you draw the resonance?
yeah,
I just want to take a quick photo.
right.
Got it. Thank you.
Yeah. Okay. So to tell if something is in EDG or EWG quickly, right? EDG versus EWG. The trend here is that EDGs will be partially negative charge or fully negative charge, right? Because the group will have a lot of negative charges or electrons to donate to be considered an electron donating group. An EWG would have a partial positive charge or a full positive charge in order for it to withdraw electrons. It wants to gain electrons, right? And then usually you'll see EDGs with a lone pair or lone pairs of electrons to donate. And then you usually see electron withdrawing groups with double bond, right? Double bond alkene or carbonyl. You also see that the EDGs, they can be R groups, which is a weak electron donating group. And then EWGs, they are halogens, X, where X could be chlorine, bromine, or iodine, because they are really electronegative, right? They withdraw electrons. R group is any like methyl group, isopropyl group, ethyl group, propyl group that donates electrons inductively, right? And then to determine if a group is an EDG or EWG, you have to look at the atom directly attached to the system, right? And then there's a whole list of them. Like there's a lot of EDGs and EWGs. Let's look at an example, right? With a diels-alder reaction here. Okay. So the system here is going to be this diene and this dienophile. Right. We have to look at the first atom directly attached to the system. So look at the EDG right here. The very first atom is that oxygen right there. That oxygen has 2 pairs of electrons and is partial negative charge, right? So that makes this whole group here an EDG, electron donating group, because it has electrons to donate into the system, donate into the diene, right? If we look at the other group here, the very first atom attached to the dienophile, the dienophile system, is that carbon right there, right? It's not the oxygen, not the hydrogen. It's that carbon right there. Then when we see the partial charge of that carbon, that's partial positive charge. So if that's partial positive charge, it wants to gain electrons, right? Because it's missing electrons. This partial positive charge means that it's missing electrons. So that means it wants to gain or withdraw electrons. So this is an EWG, right? There's a lot more EWGs and EDGs out there, which you will have to be comfortable with for especially chapter 15 and 16 with the benzene reactions, ortho paradirector, meta director, right? But this is how you tell if a group is an EDG or EWG. Look at the very first atom attached to the system, right? The system could be either the dienophile, or the benzene, right? So that's an EDG, that's an EWG. Now we're going to talk about the regioselectivity of this right here. I'm going to draw in the resonance structure of this diene. We said that that is an EDG, which can donate electrons into the system. So when it donates electrons, we're going to get this resonance structure here. Right. Now this is an EWG, so it's going to withdraw electrons from the dienophile and pop that double bond onto the oxygen to get this resonance structure here. So a lot of resonance structures are going to come back. Right. But when you do this reaction here, you don't have to draw out these resonance structures. It's just to help you visualize where things are supposed to be in the reaction, regioselectivity. Right? You'll see that this here is very important, what I'm doing right now, right? Because the reason why we're doing this is because we're going to see the pocket between the diene and the dienophile, right? The pocket that's going to get formed, the bonds that are going to get formed between them. That's the pocket right there, right? We want the charges to be aligned, right? This negative charge is attracted to that positive charge because they're opposite. So that makes this aligned. So the reaction can go through normally, right? So the reaction can go through now, right? I'm not going to go over the stereochemistry yet and the exo row. I'll get back to that, but right now we're focused on the regiochemistry of this, right? Where things are supposed to be, right? I'll give you an example now where there's a problem, right? Boom, boom, boom. Yeah, there's a lot of things going on in diels-alder, but let's keep this straight, right? You gotta worry about the regioselectivity of this reaction, the stereoselectivity reaction, and so much more, right? So let's look at this one right here. Is this going to be considered an EDG or EWG of the diene? Right. So this is the diene system here. This is the dienophile. Is this NH2 considered an EDG or EWG?
EDG, right? Because it has electrons.
Yeah, it's EDG, right? Because the first atom directly attached to the system is this nitrogen atom right here, which has 1 lone pair of electrons and is partial negative charge that is able to donate electrons. That's the exact definition of EDG, electron donating group, right? So that first atom is partial negative charge, EDG, donate electrons, boom, 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 draw the resonance structure, like that, boom, and H2 plus. This first atom here directly attached to the diene file, right? Don't look at the oxygen, don't look at the hydrogen. Those are not the first atoms directly attached to the system. It's this carbonyl carbon right there, right? Which is partial positive charge, making that an EWG. It wants to withdraw electrons. So it's going to withdraw electrons like that. Pop that up there. But let me actually label this. This is an EDG. This is an EWG. Boom, boom. Okay, now let's look at the pocket between the diene and dienophile. Now we see a problem here. The problem is that the negative charge of the diene does not align with the positive charge of the dienophile. They're misaligned now. They're on opposite sides of each other, opposite ends of each other. So this is misaligned. Right. So some people, they will lose points by just going through with the reaction. But this reaction as drawn cannot go through as it is right now because the charges are misaligned. Right. Another way you could see that is that let's draw in the original structures again. We see that there's a partial negative charge up there from the resonance structure, partial positive charge up here from the resonance structure, partial negative here, partial positive here, right, at the end. We see that there's a repulsion between those charges, right? Because like charges repel each other, opposite charges attract each other. So that's not good. So if you see that on the reactions, predicted product problem, you have to flip one of them to make them aligned. And I like flipping the dienophile because it's easier to flip, it's smaller. So I'm just gonna flip it upside down like this. Right. So now once that's flipped upside down, and then I draw in like the resonance structures to show you guys more clearly why this will work now. Now we see that the charges will align. Okay. Now they are aligned like that. So now the reactions can go through normally. Okay, so that's one of the regional selectivity reactions of it. There's another one where if the dienophile has two groups. Well, I'll go over that when we go over the stereoselectivity. Let's go over the endo rule now. Endo rule or stereoselectivity. Actually, I'll just do the participation question that Jane sent me right now, and then I'll complete the rest of this diels-alder reaction in tomorrow's office hours. Right, because there's a lot of things going on diels-alder, but let's do the participation that Jane sent to me earlier, which is this problem right here. And explain to you diels-alder in this way. Right. Okay. So that typo? Is did anyone mention a typo about this participation problem? Because I don't think this double bond is supposed to be here. I don't think it's supposed to be there. I think there's supposed to be two double bonds, one here, one here. Did anyone mention about that on like Piazza or the Levens say anything about this participation problem?
I don't think so. I'll check for you right now, but
Yeah,
I don't
yeah.
know if anybody's that far yet.
Oh yeah, is this like the most recent lecture?
Yes. I
Oh shoot,
think
no, you guys
so.
have lecture tomorrow.
We just talked about I think.
Yeah. Because this looks weird. It was like that. It's not supposed to be like that. Okay, so I think soon, like someone will mention that there's a typo here. That double bond is not supposed to be there. This is supposed to be a diene right there. Right. In order for this to be the diene and this to be the dienophile. Right. Okay, we're gonna go stick with that to get the right products. Now let's draw that pocket between the diene and dienophile like this. Right. Whatever is inside the pocket, which is this group right here, that's called the in group. Whatever is outside of the pocket, which are these groups right here, those are the out groups. Okay. Now we see two EWGs here, right? Because if we look at the very first atom attached to the dienophile, it's the carbon that is partial positive charge, right? This carbon is partial positive charge because it's attached to an electronegative nitrogen, electronegative fluorine. So those are two electron withdrawing groups right there, right? So when I draw in the arrows right here, boom, boom. Oh wait, what am I doing? Okay, boom, boom, boom. This is what I would get here. Right, so that's the base product that we get, the cyclohexene. But the way that Levens is drawing this here is in a different format because we see that these in groups here, imagine it going up now, right? Because we're making cyclohexane. Like let's number this 1, 2, 3, 4, 5, 6. Like we did at the beginning when I showed you guys the basics of this diels-alder reaction. That's this 1, 2, 3, 4, 5, 6 carbon chain. So that's the skeleton, the base skeleton structure of this, right? We see that between 1 and 4, it's a CH2 group, right? So we have to maintain that CH2 group there somehow. That's going to be the CH2 group bonded like that, right? I drew wedge bonds here to show that it's going up towards you. So there's another ring here. That's called a bicyclic ring. 2 rings in a molecule together, right? I'll redraw it in the way that Levens wants you to draw it in, or the way that Levens puts it in her problem sets and exams. But this is the same thing, right? That ring right there is this wedge CH2. It's a wedge because it's going up towards you, right? And that was always there, which is the CH2 right here. Let me highlight that to make it more clear. Let's highlight it purple. That CH2 part, which is the CH2 part right there, between 1 and 4, between atoms 1 and 4, right? Okay. So we didn't talk about the endo rule yet, but this is what the endo rule is talking about. The out groups are going to be cis, the same side, to the EWG. The in groups are going to be trans to the EWG, right? And we'll go over this more in detail tomorrow. The endo rule is going to be the kinetic product. And then something called the exo product is going to be the thermodynamic products. Okay. The kinetic and thermodynamic is like you have to before like doing this, you have to like do the hydrohalogenation reaction with the hot cold temperature, right? But then to predict the product, you just need to know this right here: out group cis to EWG, in group trans to EWG. Okay. So if I made the CH2 bridge my wedge, the dash is going to be the methyl and this ethyl, right? The methyl groups on carbons 2 and 3 stays as a methyl group. flat and planar, no wedge, no dash, because carbons 2 and 3 here stays as an sp2 carbon that's flat. Right. Now, we said that the methyl and ethyl group was the out group, right? And based on the endo rule, they have to be cis to the EWG. So that makes the CN and CF3 also dash in order for them to be cis to each other, the same side to each other. The out groups here have to be cis to the EWGs, like that. Right? So that's one of the products right there. The other product could have came from if we flipped the dienophile to get this right here, right? Because when we do resonance, we get positive charges on both carbons of the dienophile. So the second product is going to be when you have the flipped dienophile to get this product here, the second product here. The CF3 is now on the top. The CN is now on the bottom. Let's draw this in Lieben's way now. Right, which you could see the bicyclic ring more clearly in this way, in this projection. Right, where this is going to be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We see that between 1 and 4, there's that CH2 bridge right there. CH2 bridge right there, which is that purple bridge. Right. Now, let's see what she puts. Yeah. Okay. Between 2 and 3, that's that double bond. 2, 3, double bond, 2, 3, double bond. Methyl group coming out, just out like that. That's flat and planar. For this one right here, this methyl group's gonna go down. This ethyl group's gonna go down. Methyl group's gonna go down. Ethyl group's gonna go down. Also, since they're cis, right? That's another important thing that I was gonna talk about, but I said I'm gonna go over it again later. This is the thing here. If you see that the two groups on the dienophile are cis to each other, they have to be cis to each other on the product, right? We see that this CN and CF3 are cis to each other. That means they have to be cis to each other in the product, which they are cis to each other here, right? They're both dashes, cis. So let's make this go down, down, CN, CF3, down, down, CF3, CN. Right, they are different products because this is asymmetrical. There's an ethyl group here, there's a methyl group there, which is why it gives us two different unique products when we flip the dienophile. So these two products here will be compounds. Let's see here. Compound H is this one, compound H, and compound F, which is this one. So F and H. Yeah. F and H, compounds F and H. These compounds are diastereomers of each other. Diastereomers. Because we see that, oh wait. No. They're not diastereomers, right? Because they have different connectivity. The CF3 on this top one here is closer to the ethyl group, whereas the CF3 on the bottom part is farther away than the ethyl group. So they are constitutional isomers. Same chemical formula, but different connectivity. Constitutional isomers, right? Different connectivity. These compounds are not racemic, right? Because they're not enantiomers. So automatically not racemic. We can go over more in detail of these diels-alder reactions, but did that make more sense on the diels-alder reaction on how I got to these products here? Which part do you guys need help with the most? So I could like note that down and then go over that tomorrow, or we could go over everything tomorrow for diels-alder with practice.
If it's okay with everybody else, I'd like to go over everything again with diels-alder.
Yeah.
Only
yeah,
because like I think repetition really helps like for it to go into my mind.
Right. And then I'll also prepare like the notes of everything you need to know as well to keep everything in order and track for you. So then you could go back to the notes and use them and reference them when you do your own practice, you know?
Thank you.
Yeah, I'll do that tomorrow. Do you want to just do all diels-alder, like strictly diels-alder tomorrow, or halogenation and halogenation of conjugated dienes tomorrow as well?
Yeah, can we do other stuff also?
Okay, yeah, hydrohalogenation and halogenation of conjugated diene as well.
Yeah.
Okay, yeah. So let's just do those three, right? Those three are gonna be the biggest parts of the second midterm: hydrohalogenation of conjugated diene, halogenation of conjugated diene, and diels-alder. Yeah. Okay. I'll see you guys tomorrow's office hours.
Thank you so much.
Yeah.
Thank you.
No
Thank
problem.
you.
No problem. See ya.